Hello, my name is Mateo, and in this video, I'm going to talk about types of failure and basics of fracture mechanics. So, first thing we're going to talk about is failure, and failure is defined as having occurred when plastic deformation reaches an arbitrary limit. And some variables that we need to know before we get into the example is SY stands for ultimate yield stress, SU stands for ultimate strength. And the Greek letter sigma stands for internal stress. So now let's take a look at the example. So let's pretend that this is a metal wire which is being elongated on both sides, right? So if that's the case, then the stress will start to increase, right? So as the wire grows in length because it's being stretched, right? And then if you were to stop um, elongating it, it will return to its normal length, right? And but if you continue to stretch it, right, then at that point, right, the stress will become greater than the ultimate yield strength, and at this point, it will exhibit plastic deformation because when it's let go, it will now be a little bit longer than the original length because you've now deformed it. It's bent now, right? Because it's a little bit stretched. It's no longer its normal size. But if you continue to stretch it past that point, right, then the stress will now become greater than its the ultimate strength, right? Which is SU, and it will break, right? So now we're going to talk about fracture mechanics, and what does this mean? Fracture mechanics is how materials fail. So this is when the internal stress is greater than the ultimate strength. So sigma is greater than SU. And some of the variables that we need to understand is that K is the stress intensity factor. And what that means is that it's the stress at the crack. And Kc is critical stress intensity factor, which is determined from standard tests. And to further explain this, there's an assumption we need to take under consideration, which is that all real materials contain cracks of some size. So this means that any material will always have some kind of a crack in it. And like it could be microscopic, so like the naked eye can't even see it, but there are cracks, and uh, this is how you have to take them under consideration. And now we're going to further explain that in an example. So now we're going to explain how it works. So if you have like a metal plate, right, we're not going to like solve an example here, but just for demonstration purposes, if this was a metal plate, um, microscopically there would be like little cracks, right? So I mean, just for scale purposes, we would pretend that's very small. But that crack would uh, it would start off very small, but then over time it would with the amount of force that is applied to it, the load and everything that's happening to this crack, it would cause for it to expand and become a bigger crack. And this is very important to understand because you need to know how to design around this because eventually the entire if there's too much stress on it, it will eventually break and you'll have critical failure. And critical failure is when uh, the material just gives out and it's done. So, um, like in class, we talked about that boat in World War II that they didn't take into account the metal and it had some cracks, and the amount of stress on the cracks eventually expanded, and then the boat just broke in half. And same thing with this plate, pretty much would happen. So that's why it's very important to design around that and to understand. And this concludes the video. Here are my references. I referenced the slides from lecture chapter 6 and the end. So thank you for watching, and that's about it. Thanks.